What is up, my chem peeps? Who is ready for another thriller of a free response? Live for this! My dreams come true every time I see a free response. Use principles of molecular structure and intermolecular forces to answer the following questions. Part A. A complete Lewis electron dot diagram of a molecule of ethyl methanoate is given below. Boom! Subpart I. Identify the hybridization of the valence electrons of the carbon atom labeled C sub W. Easy. First thing we want to do is we want to count up the regions of electron density about the atom that we're trying to determine the hybridization of. In this case, there are 1, 2, 3 regions of electron density. Remember that single bonds, double bonds, triple bonds all count as one region of electron density. And when you're trying to determine hybridization, remember that you need to be comfortable with identifying sp, sp2, and sp3 hybridizations. And the easiest way to determine the hybridization of a given atom is to sum together the superscripts of those different hybridizations and match it to the regions of electron density that you have. So this is really S1P1, which would sum together and give us 2. S1P2 sum together and give us 3. S1P3 sum together and give us 4. I've got 3 regions of electron density, the hybridization of the carbon atom labeled CW, sp2 hybridization. Boom. Side note, this is just a little shortcut method because we all know you've got so much time on the free responses. Subpart II. Estimate the numerical value of the HYCXO bond angle in an ethyl methanoate molecule. Explain the basis of your estimate. Alright, once again, we're going to be looking at counting up the regions of electron density about the atom that we're concerned with. We're trying to determine what the bond angle here is. And as it's drawn, it looks like it's 90 degrees. But again, one of the drawbacks of Lewis structures that they don't do a great job of showing us the true three-dimensional structure. So let's count up those regions. I've got 1, 2, 3, 4 regions of electron density about that carbon atom. Additionally, none of those regions are lone pair regions. Let's use PhET to help us visualize. Now, there's really more to the molecule, but imagine that this is our central carbon atom. Here's our oxygen, hydrogen, hydrogen, other carbon atom. And the chain would continue on each of these things, over here and over here. But for the purpose of this question, just focus on the regions of electron density about the atom that we're trying to determine the angle for. And since we've got 4 regions of electron density and they're all bonded regions, our bond angle 109.5 degrees. 109.5 degrees is the estimated value of the HYCXO bond angle. Okay, we've answered the question. Now let's be sure to explain the basis of our estimate. The CX atom is the central atom in a tetrahedral arrangement of bonding electron pairs. Therefore, 109.5 degrees is estimated. And you would know this because you spent countless hours practicing your Vesper theory. Moving right along. Subpart III. How many sigma bonds and how many pi bonds are in an ethyl methanoate molecule? Such a great question. Let's come back up here and take a look at our structure. Recall that single bonds are each sigma bonds. So I've got 9 sigma bonds right there and all those single bonds. In a double bond, one of those is a sigma bond, one of those is a pi bond. So in total, 10 sigma bonds, 1 pi bond. 10 sigma bonds, 1 pi bond. Boom, done. Part B. Ethyl methanoate, that's crazy, is synthesized in the laboratory from ethanol and methanoic acid, as represented by the following equation. Subpart I. In the box below, draw the complete Lewis electron dot diagram of a methanoic acid molecule. Alright, now this is not one of your standard Lewis structures. We're going to have more than one central atom. Alright, when you get to questions like this, where you have more than one central atom, use the structural formula and keep in mind, carbon will form 4 bonds, typically, nitrogen will form 3 bonds typically, oxygen 2 bonds, fluorine 1 bond, hydrogen 1 bond. Don't expect anything crazier than that. So as I start this off, it looks like I've got hydrogen bonded to a carbon. Alright, that's easy enough. I I know I can't have anything else bonded to this hydrogen because it's already got its 2 electrons. Then it looks like my carbon is bonded to an oxygen. Feeling good. My carbon has 2 bonds. My oxygen has 1. But now I've got to figure out where am I going to place this other oxygen, other hydrogen. Maybe like this. Good thought. Each of my oxygens has 2 bonds, and each of my hydrogens has 1. My carbon only has 2. So instead, I want to put my other oxygen off of the carbon, and then you choose which oxygen to place the remaining hydrogen off of. Okay, this hydrogen has 1 bond, this hydrogen has 1 bond. This oxygen has 2, my carbon has 3, and this oxygen has 1. Best way to solve this problem? Double bond my carbon and my oxygen, and then fill in the remaining lone pair electrons on your oxygens. Again, that's not easy, and you may be confused about why I did that. But without going into a huge amount of organic chemistry, I think the best rule when it comes to coming up with Lewis structures like this is simply thinking about how can I get hydrogen to have 1 bond, carbon to have 4, nitrogen, if you have it, to have 3, oxygen to have 2, and fluorine, if you have it, to have 1. If you keep those rules in the back of your mind and you use the structural formula, you have a pretty good shot of coming up with the Lewis structure. You'll generally have to do it with these elements that strictly follow the octet rule, except of course hydrogen. So it just takes practice, don't panic. Subpart II. In the box below, draw the complete Lewis electron dot diagrams of a methanoic acid molecule and a water molecule in an orientation that allows a hydrogen bond to form between them. Alright, first I'm going to redraw my methanoic acid molecule that I just drew up in the box above. Next, I'm going to draw my water molecule. Now to help you understand this, I'm going to draw in my dipole for my water molecule. We've got slightly negative and slightly positive regions of this water molecule. We want to think about where could this thing potentially hydrogen bond with my methanoic acid molecule? Where is there going to be a slightly positive or slightly negative region? Well, we've got a dipole here. There's going to be a slightly negative region up here, slightly positive region down here. We're also going to have a slightly negative region by these lone pair electrons on my oxygen, slightly positive region by the hydrogen. Again, that's because the oxygen is super electronegative. Again, you want to make sure that you draw it with the correct orientation. So if I draw it here, I want to make sure the negative end of my water molecule is facing the positive end of the dipole on my methanoic acid here. And then I would draw in my hydrogen bonding as a dashed line. But that's not the only way you could do it. Remember, when you have hydrogen bonding, hydrogen must be covalently bound to fluorine, oxygen, or nitrogen, because those elements are very, very electronegative and really pull the electrons in the bond, creating very strong partial positive and partial negative regions, which creates that very strong type of intermolecular force hydrogen bond. Have a fantastic day.